Okay, a real quick side step into quantum tunneling. So we've got two different quantum systems that we've looked at so far, particle in a box and harmonic oscillator. Particle in a box, I'm showing the n equals 2 quantum state. And so the wave function that we get an energy associated with n squared h squared over 8ma squared. And so this wave function has restrictions on it that it equals psi of x equals 0 at the boundary. It cannot exist on the outside of the, or outside the potential. Okay, so for our quantum oscillator, however, the potential barrier is really what's dictated by the potential energy. Because remember, for the Hamiltonian, we had minus h bar squared over 2m d squared dx squared plus 1/2 kx squared. This 1/2 kx squared is the potential that's restricting the wave function and dictating what the higher energy states are going to look like. This wave function, or this wave function has a Hamiltonian operating on it, which is minus h bar squared over 2m d squared dx squared plus 0 because there is no potential energy. Okay, so the wave function actually has, if we zoom in over here, I'm going to draw this. So here's this picture, and here's my wave function coming in. So there's actually all of this space right here that actually is non-zero outside the boundary. Okay, whoops, underneath. So there's my potential energy. The wave function doesn't go to 0 at the boundary like it does for the particle in a box. That's why we start with the particle in a box, because it's much simpler, because the wave function has to be 0 at the boundary. The fact that this is non-zero at the boundary, so the integral of psi squared dx, which is our probability, is non-zero just outside of the potential barrier. And for the wave function of a harmonic oscillator, I think Atkins calculates it out. This is example 7E.3, calculating the tunneling probability for the harmonic oscillator. Turns out to be about 8% of the wave function can exist outside of the barrier. That's pretty huge. That's pretty big. Now, granted, for the n equals 1, a lot of the wave function is in the middle, and so 8% of it exists on the outside, so it's about 4% on each side. But on this particular case, there's a lot more wave function in the middle up here, and so less of a percentage is going to be tunneling outside of the barrier. But it's actually much more significant for the lower energy states. And for vibrational states, pretty much every vibrational state's in the ground state. So this is going to make a big difference pretty soon when we get into chemical bonding, because a lot of bonding occurs because these wave functions are going to have slight overlap, which means they have slight probability of existing. And if they have slight probability of existing, they have slight probability of overlap, which means you have a way to get wave functions to overlap. You have ways to get molecular bonds to form. Cool. Cool. So that's pretty much probability existing outside the barrier, which is also called quantum tunneling. It sounds so much fancier than it really is. Cool. Okay, that's all I got for that.